electric current. It is one of the very important concept of the topic current electricity. So, it is the matter of 19th century. The matter of 19th century. Scientists Drew and Lawrence proposed that metallic conductors contain large number of free electrons. At the same time, positive ions are fixed in their locations. It means, suppose this is a conductor, it contains large number of free electrons. Free electrons means those electrons present in the valence shells. When the electrons are moving, leaving their atom, that means in their back they are leaving the positive ions. So, the arrangement of these positive ions, we say lattice state. The arrangement of positive ions in their locations is called lattice state. So, you assume that now this metallic conductor is in a open circuit. It is not connected to any circuit. Now the conductor is in open circuit. When it is in open circuit, these free electrons, they move different directions. They move randomly in any directions in their will and wish. There is no doubt at all. But I want to say that we are discussing about the motion of the electrons in the lattice state. How the electrons behave in lattice state. So, for example, we will take this area of cross section. You know the area of cross section in the sense the surface of the plate which is exactly perpendicular to its length. We say that is the area of cross section. So, if I assume this is the area of cross section, the number of electrons, free electrons moving from left to right is also equal to number of electrons moving from right to left at this cross section at a particular time. That means the number of electrons moving from left to right through this cross section is also equal to number of electrons moving from right to left at the same time. That means the net amount of charge flowing through this cross section is 0. The net amount of charge flowing through this cross section is equal to 0. So I can say that there is no flow of current. Now the conductor is in open circuit. It is not connected to any circuit. It is simply a piece of metal you can consider. The electrons are moving, but there is no current. The reason is that electrons are moving randomly in any direction. So at any point, any cross section of conductor, the net charge flowing through it is equal to 0. This is the reason there is no electric current in this metallic conductor. Now question comes, what happens to the motion of the electrons if this metallic conductor is connected to a battery? Now I am going to explain what will happen if the metallic conductor connected to the battery. See here, children. This is the conductor. Now I am connecting it to a battery through a tap key. Suppose there is an electric bulb. Now when the switch is on, we will observe that bulb is glowing. The reason is that there is transfer of energy from the cell to the electric bulb. Who is responsible for this transfer of energy? Definitely, electrons are responsible for transfer of energy from this cell to this electric bulb. As a result, we found that bulb is glowing. If there is flow of electrons, there must be ordered motion of electrons. Earlier we discussed when it is not in the circuit, electrons are moving randomly in any direction. But now it is connected to a battery. There is an electric field. So the electrons start moving in a specific direction. As a result, energy transferred from the cell to the bulb. We found that bulb is glowing. So I can say that there is an ordered motion of electrons. So that ordered motion of electrons constitute the electric current. So I can say that the rate of flow of charge constitute the current, or I can say that the directed rate of flow of charge rate of flow of charge through any cross section directed rate of flow of charge through any cross section of a conductor is known as electric current. I can say that rate of flow of charge is electric current. If I want to write mathematically, I can write that I is equal to Q by T, where I is for the current, Q for the charge, T for the time. I can write it is equal to, here N is the number of charge particles, E is the charge of electron. So I can say that I is also equal to LE by T. Here Q stands for charge, T stands for time, I stands for current, E stands for charge of electron, N stands for number of charge particles. So, what about the unit of current? The SI unit of current is ampere. Shortly, we can use as A. So, if charge is 1 coulomb, suppose the charge is 1 coulomb, time is 1 second, then the current will be 1 ampere. So, generally we use the SI unit of a current, except that it has also CGS unit. So, I want to say 1 ampere means what do we understand? Ampere is the amount of current when flow of charge through any cross section per unit time is 1 coulomb. So 1 ampere is the amount of current when flow of charge through any cross section per unit time is 1 coulomb. So the unit of a charge is coulomb in a SI system. Unit of current is ampere. Except that electric current also has CGS unit. In CGS unit, we say start ampere or we say half ampere. Start ampere or we use half ampere. This is in CGS system, but throughout the topic we will not use the CGS unit, we will use the SI unit of current. Okay children? So, now the concept of current, I hope it will be clear for you now. One more important concept I am going to explain, that is the drift velocity. Before saying the drift velocity, it will be better we will discuss about the different types of electric current. So, types of electric current. Generally, there are two types of electric current based on its magnitude and direction. Based on magnitude and direction, there are two types of current. One is direct current, one is alternating current. Direct current, we write it as DC current. Alternating current, we say it as AC current. Two types of current based on its magnitude and direction. Okay. So in DC current, what happened? The magnitude and direction do not change. DC magnitude and direction do not change. But so far as AC current is concerned, its magnitude changes as well as direction also changes. Okay, so I can say that magnitude changes continuously and direction also changes periodically. This is the case of the DC current where the magnitude and direction do not change. So what are the sources of DC current? Can you say what are the sources of DC current? Battery, dynamo, DC dynamo, the cell what you are using, they are the examples of direct current. Whereas dynamo is an example of source of alternating current. Okay children, but for your 10th class, whenever we use the circuit diagram, we don't use the AC current. All time we use the cell or battery. That means we use the DC or direct current. Okay children, so before explaining drift velocity, I think we'll go through one numerical problem which will make your concept more clear. See here, for example, a charge of 40 microampere I have written to you for the charge. A charge of 40 microampere, suppose flowing through a conductor or flowing through a circuit for a period of 5 seconds. Charge is 40 microampere. Sorry, sir. Charge is 40 microcoulomb. Time is 5 seconds. You have to find out the average current in the circuit. You have to find average current in the circuit. So you know that I is equal to Q by T. This is equal to 40 microcoulomb. I can write that 40 into 10 to the power minus 6 coulomb divided by time. Time is equal to 5. That means 8 into 10 to the power minus 6 ampere. So I hope that your concept regarding the current is clear. But one more question comes to my mind. What is the direction of current? Is it a vector quantity or scalar quantity? Definitely, current is a scalar quantity. In fact, it is not a scalar quantity. But so far as 10th class is concerned, we will use it as a scalar quantity. In higher classes, you will study that it is a tensor quantity. Tensor quantity means it has a unidirection. All the time it flows from higher potential to lower potential. But that matter we will study in a higher classes if you take the special physics. But so far as 10th class and class 2 is concerned, we will consider current is a scalar quantity. Why I am saying it is a scalar quantity? You know that lower classes, any physical quantity which has both magnitude as well as direction, we say it is a vector quantity. But these two things are not enough. If magnitude is same, direction same, simply we cannot say a term is a vector. A term will be vector if it follows the law of vector addition. That means in addition with magnitude and direction, if the term follows the law of vector addition, we can say it is a vector. That means law of vector addition in the sense parallelogram laws of addition, triangular laws of addition, what we study in the plus 2 level. Except magnitude and direction, if it follows the laws of vector addition, we can say it is a vector quantity. But actually, it does not follow. For example, you see, this is the point through different directions coming to this point. The total current in this point, simply we add. We don't think about the vector addition of the current. Just the resultant current or net current is the algebraic sum of the current. We don't think about the vector addition. So I can say that current is a scalar quantity. So earlier I might have mentioned your charge is also a scalar quantity. Charge is a scalar quantity. Current is also a scalar quantity. So now I shall move towards the drift velocity, which is one of the very important concept in current electricity. So before explaining the drift velocity, it will be wise to remind you about the thermal velocity of free electrons. Thermal velocity of free electrons. Listen carefully. What is thermal velocity of a free electrons? You know that in a metallic conductor, electrons move randomly with a very high speed. That speed is called the thermal velocity of free electron. When the conductor not in open circuit, electrons move randomly with very high speed. That speed is called the thermal velocity of free electron. That is due to the heat, that is due to the temperature. Electrons get that momentum. Okay, so I can say that the average thermal velocity of free electrons average thermal velocity of free electrons in any direction is 0. Listen carefully. So I said that the velocity of the free electrons in a metallic conductor is very high, which is called its thermal velocity. But average thermal velocity of free electrons in any direction will be all the time equal to 0. So now I shall move towards the drift velocity. It is one of the important concepts for 10th class as well as for the second year plus 2. Now, suppose this metallic conductor now connected to a battery. See here. For example, this metallic conductor I connected to a circuit. What happens? Immediately one electric field develops. As a result, electrons start to move. From where? From the negative terminal to positive terminal, there is no doubt at all. So I can say that drift velocity is the average velocity with which the free electrons get drifted towards the positive end of the conductor. So it is better I shall write, then I shall explain. The average velocity with which free electrons get drifted towards the positive terminal under the influence of an external electric field. The average velocity with which the free electrons move or get drifted towards the positive terminal under the influence of an external electric field applied, that is called the drift velocity. Listen carefully. Whenever electrons move in this conductor towards the positive terminal, you see that these electrons are are influenced by certain force. There is no doubt at all. For example, you see that this is the length of the conductor we are discussing. Inside this conductor, number of free electrons are there. Those electrons are moving from negative terminal to positive terminals. This is the direction of a flow of electrons from negative terminal to positive terminals. So these electrons experience a force that is equal to, so what is capital E? Here capital E stands for electric field. E stands for charge. So the electrons, those are moving, they experience a force, no doubt at all. Okay. Now you see that earlier we discussed how the electrons are behaving in the lattice space. When the electrons are moving from one point to another point, definitely they will be attracted by the positive ions. If they will be attracted by the positive ions, definitely their speed will decrease. But the electrons cannot stop. The fact is that there is an electric field. Again they start to move. That means I want to say that electrons get the acceleration. Its speed increases, sometimes it decreases, but we consider its average speed as the drift speed or as the drift velocity of the electron. Now listen carefully. So I said that the electrons, those are moving inside this conductor, they are influenced by a force due to presence of this external electric field when it is connected in a circuit. So that force is the product of E into E. Here small e stands for the electric charge, this charge of the electron. Capital E stands for the electric field. Now I said that whenever they are moving from negative terminal to positive terminal, they are experiencing a force. Their speed also increasing and decreasing, but we are considering their average speed as the drift speed or drift velocity of the electron. Now, if they are getting the acceleration, then what is this acceleration? Definitely this acceleration is equal to force by mass. Already we know. So I said that force is E into E. I have written here, and suppose it is better I shall mention like this. It represents mass of the electron. Okay. So under the influence of this electric field, the electrons move, no doubt at all. But when one electron moves, during that time they collide with the positive ions, because the positive ions are fixed there in place. Suppose one electron starts from here. Here is a positive ions. It collides with it. Okay. So that means its speed decreases. It spent some time here. The time it spent between two successive collisions. Suppose one time it collided. Again one more time it came and collided here. So definitely there is a time gap between two successive collisions. So the time between two successive collisions we say relaxation time. Listen carefully. Electrons are moving, but they will be influenced by the positive ions. They will attract. So they may collide. So the time between two successive collisions is called the time between two successive collision is called relaxation time. It is represented by the letter tau. now listen carefully. So there are number of electrons are there. Suppose the velocity of the electrons just before the collisions are u1, u2 like that. Okay, these are the velocity of the electrons just before the collision. Okay, that means I can say that this is the initial velocity of the electrons. It is better to say that it is the initial velocity of the electrons. So when the electrons comes in contact with the positive ions, their speed decreasing. The speed just before collision. Speed just before collision. Let it be V1, V2 like that. This is the, you can consider like your final velocity. We know that from equation summation V is equal to U plus AT. So here I can say that V1 is equal to U1 plus A tau 1. In place of t, I am using the tau. This is the time of relaxation. Similarly, I can say that Vt2 is equal to U2 plus A tau 2 like that. So, if I want to find the drift velocity, I said drift velocity is nothing but the average velocity. So, drift velocity, or I can say it is the average velocity. Drift velocity. It is a vector quantity. I can put this arrow mark also. If I have not mentioned any places arrow mark, but velocity is a vector quantity. See that. I can write this is V1 plus V2 if n is the number of electrons. So I can write it like this: U1 plus A tau 1 plus U2 plus A tau 2 plus Un plus A tau n divided by n. So I can write this is U1 plus U2 plus Un divided by n plus A tau 1 plus A tau 2 plus A tau n divided by n. So this is equal to 0. Why? Already I said that the thermal velocity of the electron in any direction is equal to 0. That time I said that U1 plus U2 up to Un, if you add that, that is the thermal velocity is equal to 0. So I can write that 0 plus A into tau 1 plus tau 2 plus tau n divided by n is equal to A into tau. This is the drift velocity. So in place of acceleration, I can use this is minus E divided by mass of the electron into tau. Earlier I said that acceleration is equal to force by mass. Force is here product of small e and capital E, and m I have mentioned for the mass of the electron for your convenient. So this electric field is also vector quantity we can mention it as a in the form of a arrow mark, no doubt at all. So children, this is about the drift velocity, or you can say this is the average velocity in which electron drifted towards the positive terminal under the influence of an electric field or external electric field. Now one more term I shall explain, that is the relationship between drift velocity and electric current. It will be made more clear over this drift velocity. So relationship between drift velocity and electric current. Relation between drift velocity and electric current. This is a small concept, listen carefully. Suppose we are considering a conductor. This is the conductor. Suppose its length is L, its area of cross section is A. Then what will be the volume of the conductor? Volume of the conductor, I can say volume of the cylindrical substance is the base area into height. Here base area means area of cross section, height means its length. So I can say volume of the conductor is equal to A into N. Suppose N number of electrons are present in unit volume. N equal to number of electrons in unit volume. Suppose N is the number of electrons in unit volume. Then total charge in this conductor definitely will be N A L E. Listen carefully. Total charge is, already we have studied, N into E. The total volume is equal to A into N. So the amount of charge flowing through this conductor will be equal to N A L E. L is the length of the conductor, E is the charge of the electron, A is the area of cross section, N is the number of electrons present in unit volume. Okay, so under the influence of this electric field, definitely the electrons move means there will be a current, and when it moves from the distance L from one point to another point with a certain speed, definitely it will take some time. So already you know that time is equal to distance by speed. The distance is A, speed is drift speed, or you can say the drift velocity. So I can write that T equal to L by Vd. It stands for the drift speed. If I think about the current, I is equal to Q by T. Listen carefully. I is equal to Q by T. In place of Q, I shall use, this is N A L E divided by time. Divided by time. So already I have mentioned this time is equal to L by V D. Clear? Then how much left if I cancel that? See that N A L E into, so L cancel, this is equal to N A E B D. This is the relationship between electric current and drift velocity. I is equal to N E A V D. This is the relationship between current and drift velocity. Children, for today our concept I think might be clear. So definitely in the next video we'll discuss many more concepts of this current. Jai Hind.